Okay. All right, well, thanks for coming out today. I know it's the end of the semester, so on one hand, we're all busy, but then on the other hand, a lot of people might be extra credit. So, I guess it's a wash. But I mean, we certainly have a lot of interesting weather going on. So today we have Mrs. Erin Cobbett from GPC's Office of Climate Institutional Research and Planning. And actually her background is in meteorology, so I hope she's excited to be able to talk about that today, because at her job she's doing more like number crunching and doesn't have much to do with meteorology these days. Yeah, she did her master's in aeronautics and aviation meteorology. Where?
Embry-Riddle Aeronautical University.
Oh, okay. So then, welcome to Erin, and she can go ahead and get started.
Thanks, everybody. I am happy to be here. As she said, I don't get to do any meteorology in my current job, so this is really exciting for me to be able to talk about it. It's something that I've always had a huge passion for, and that's why I got my degree in it. Amongst other things in college, I love meteorology. It's a combination of a lot of great fields, and I find it fascinating. I think a lot of people who are in meteorology are big weather nerds. I'm definitely not any different. So what I'm going to talk about today is some common meteorology myths. And when I say that, I don't mean sailor's delight, red sky tonight, that sort of thing. Those are more urban legends. What I'm talking about today is a lot of things that I hear all the time with a degree in meteorology, which we will get into right now. The first one of which sort of irks me a little bit. Meteorology is not, in fact, a study of rocks, or space rocks, or rocks of any kind. People who study space rocks are usually astrophysicists, astronomers, people who are even much smarter than me, and like physics a lot more than I do. I like applied physics. But meteorology then is the study of the atmosphere and the phenomena that occur within the atmosphere. Originally, it came from Greek, from the word meteoron, which means things that happen in the atmosphere, something that happens high in the sky. And like I said, it is an interdisciplinary field of physics, math, chemistry, engineering, and computer science. So it has a lot to do with a lot of things, but not space rocks. So that was quick and easy. The second myth, weather is not important, which is really easy to say because we talk about weather in our everyday lives, but we don't think about it maybe in the sense that it is a science, and I consider it to be a hard science. That could be debated. But it happens and it affects our daily lives. These are some current pictures, well, they're more current, of Hurricane Sandy that happened in October. On the left, we see Hurricane Sandy from October 28th, and on the right, Hurricane Sandy a day later, but it was covering 1.8 million square miles, which is a huge amount of area for a storm to cover. And inherently, we know that weather is important and weather costs a lot, not only in dollars, but in lives. This is a chart from NOAA, which is the National Oceanic and Atmospheric Association. They govern everything weather-related that happens in the United States. They're a governmental body for weather. Under that is the National Weather Service, who actually has care of producing the forecast for everything. But this is a chart that NOAA produced that shows 2012 billion-dollar weather and climate disasters. As you can see, there were quite a few. One of the ones we were most familiar with was Hurricane Sandy. Official numbers have still not come out yet, but it has been associated with 131 deaths and over $65 billion of damage, which is a considerable amount. The same report that estimated that, this was a global reinsurance company, estimated that a cost of Midwest droughts that happened in 2012 were $35 billion and also associated with 123 deaths. And since 1980, NOAA estimated that the United States alone has sustained 144 events where damages and costs reached or exceeded $1 billion. So it's a huge amount of money, and every year this happens. And we should know, and maybe we don't, But meteorologists save lives, and they do that through things like watches and warnings, and they provide the public either through the use of TV weather forecasters, the internet, your mobile phone. We have a variety of devices now available to us that give us weather information on all of these things, some of which I feel most people don't even know that NOAA actually has charge of, especially minute things, more like freezing spray and drought condition. Oh, drought is not really a minute thing, but you might not think about that in your everyday life. You think of, oh, it's going to rain today, oh, it's going to snow today, but they have charge of a huge amount of things to do every day. And if you are still not convinced, NOAA produced a report that over the 10-year period after they implemented NextRad, which is weather radar, tornado-related deaths were reduced by 34%, injuries by 45%, and it was estimated a cost savings of $3.2 billion. So with one piece of technology, we saved a huge amount of money and a lot of lives, and we still do. So, I cannot tell you the amount of times I have heard something to the effect of, the weather person's wrong again. It must be nice to have a job where I can be wrong every single day and not get fired. These things I hear all the time, including my mother. You should really come forecast in Denver. You do a better job. No, I wouldn't. It's very difficult. Let me just put that out there right now. And we're going to cover some of the reasons why that is difficult. So to start with, you might know, but the Earth is a really big place. Really big. And you can see some of those numbers up here. The United States alone only covers about 2% of the total area of the Earth. And that's something that we know is big, and we live in it every day. But why are you telling me that the Earth is big? I know that. Well, you need a reminder, because some things we don't think about. And most of you have probably heard of the butterfly effect, or something that happens in, say, Buenos Aires, the butterfly flaps its wings, causes a tsunami in India. Well, in weather forecasting, this is certainly true. What happens in other parts of the globe has a trickle-down effect, a ripple effect, and can definitely affect the weather across the globe. But it makes it really hard to forecast when you have an area of 196 billion square miles. So how do we begin to even forecast? Well, we need a few ingredients first to start with. One of the main things that we use are observations, or our data points, and those come up from a variety of sources. We have data from satellites, from radar, we get vertical data through the atmosphere from weather balloons. We have land stations all over the United States as well as the world, and those give us things like temperature, dew point, sky cover, all kinds of things. Buoy data gives us sea surface temperature, temperature below the surface, also relative humidity and temperature over the ocean. And then we have satellites that give us space weather, which is a whole other talk in itself, and I won't be going into that in detail. But the space weather certainly affects our life here every day on Earth, and it does affect our weather. And just as a little fun fact, the NASA Solar Dynamics Observatory is the one that we see a lot now. The solar flares have begun to start up again, and that's the satellite that produces that. One of them. Other forecasting ingredients, beyond our daily our daily points, we need climatological records, which are a long time of records, thousands of years, or even a week's worth of trends. But we have to have those records to put into our forecast to help us forecast the future. We also put things in like previous forecast information. So this past week, how accurate were we at forecasting temperature or dew point? And what is the degree separation that we were off, and why were we off? And then, last but certainly not least, we have our handy-dandy friendly computer, which provides us with computer models, which are absolutely crucial to our forecasting abilities currently. And in those computer models, we use the equations of motion, which we'll talk about a little bit in a couple of slides. With lots of math and lots of equations and lots of computing power. So those are our ingredients. So how do we do it? Well, we have several methods that we can use to forecast. The first and most simple is the persistence method, which basically assumes that the forecast conditions from today to tomorrow will not change. So if today it's 55 and rainy, tomorrow it will be 55 and rainy. This works great in places like California, where it's always 70 and sunny. It doesn't work well here, or in Florida, or in other places. It also works well in the short term, 1 to 2 day forecast, because truly the conditions don't change a lot between day to day, but longer term forecasts, like 3 to 5 days, are going to vary a lot more. Then we have our trends method. And that basically assumes that we understand the speed and direction up front. We know where the locations of highs and lows are. And we can calculate them and figure out where they're going to be based on how fast they're moving. So as an example, if a storm is 1,000 miles west of us, it's moving at 200 miles an hour, it can arrive in 5 days. It's fairly simple, but requires a little bit more meteorological knowledge. So the climatology method. So basically what we do is take our long-term range of records and we forecast it using the average for today. So if we have 1,000 years of data that said on December 25th, the average temperature was 35, we would say, well, this December 25th, it's going to be 35. And then the most complicated of the methods is numerical weather prediction, or NWP. And that's where we get into computer modeling and computer modeling forecasting. And again, lots of computer power, lots of math, and lots of equations. So we have all these methods. What do we do with them? Modern forecasters use a combination of both, mostly because we can. And it's much better when we combine methods. We start usually as the base is NWP, and then we bring in climatology, and we look at our trends, and we look at persistence, and we're able to form a more complete picture of what's actually happening. But we all know our computers are perfect, right? And they perform perfectly 100% of the time. So why wouldn't we just have a computer do it? Well, we obviously know that that's not true. Computers are not perfect, and they're far from it, especially when you're dealing with the amount of data, observations, formulas, and calculations that we're dealing with to create a perfect forecast. So, a model. What is a model? A model is the equations of motion, which I've mentioned, but those are the conservation of momentum, conservation of mass, conservation of energy, and the ideal gas law solved to make a model of the Earth's atmosphere, and that's how we predict the future. We time step out this model into the future based on selected hours into the future, 12, 24, 480, and then we're able to see what the model thinks is going to happen that far in advance. As an example, on the left is from the National Center for Environmental Protection, who does a lot of our modeling at NOAA. And this is an ensemble forecast. We call this a spaghetti plot, as you can probably see why. It's all the models combined into one plot, and then they average them to find out where we think it actually might occur, whichever field it is. So, but you can't understand tomorrow if you don't understand today. So one of the ways that we observe our weather, and the most notable for surface observation, is our ASOS stations, or Automated Surface Observing Systems. We have 900 of these across the United States. They operate 24/7, 365, constantly collecting data, but they report about 12 times an hour. They collect sky condition, visibility, weather type, pressure, temperature, dew point, all kinds of information on wind speeds and directions, as well as an accumulation of precipitation. At the bottom, where it says KATL, that's what the ASOS produces. It's called a METAR, and most of our pilots and anyone related to aviation uses that constantly, but it's also fed into our models to figure out everything that we need from surface observation. As you can see, it is coded. I have thought about breaking it down, but that's another presentation in itself. But it gives you all the information you could possibly want right at the surface. But there's a big problem with these. As much information as it does give us, if we look to the map on the right, on the bottom, you see a map of Georgia with lots of colored pins. And that's all the locations of the ASOS stations in Georgia. It looks like a lot. But when we blow that up, which is the top map, we see the 3 main ASOS stations that serve the Atlanta area. Now, if you've ever been in Atlanta for any time, driven around Atlanta, you know that the difference between Chamblee, Tucker, the airport, downtown Atlanta is huge. The environment, the conditions, everything changed a lot within even a 50-mile radius. But what that means is that we're not getting coverage of those areas, and that's not being put into our models. A very common phrase is garbage in, garbage out. If we can't observe the surface perfectly from the start, we're not going to be able to forecast it. Another example, this is another observation, is our radiosondes, and this is how we get pressure, temperature, and relative humidity, amongst other things, through the vertical in the atmosphere. We send them up via a balloon, they're also known as a weather balloon, and they radio back the information. As we said, the ASOS stations, we have 900 in the United States alone. These we have 900 worldwide. So if you can imagine the separation between those stations, it's humongous. And they're only sent up twice a day, whereas the ASOS stations, we can get readings 12 times an hour. So we have much less spatial and temporal coverage in the vertical than we do on the surface. An example of what the radiosonde can produce is on the right-hand side. That's a diagram that we can produce from the information. It's called a QT log T. It gives you your pressure coordinate on the left-hand side, temperature across the bottom, and wind speed and direction along the right-hand side. It's very fun to diagnose. It becomes very complicated. So, that's our problem one. We don't have enough observations spatially or temporally. And what we have now is so much better than what we used to have. Problem number two, the atmosphere is complex. A lot of that complexity lies near the surface. Things like tall buildings, runways, even oceans and small storms create a lot of complexity for models that they really can't handle. There's a lot of these little features everywhere, and there's just too many of them, and they're too small. So what we have to do is parameterize, and the models idealize the atmosphere, so we can still get a model that works and runs, but it's definitely not 100% accurate. So we parameterize those small-scale features, and we also do things that are complex or poorly understood physical processes, some of which include turbulence or air mass thunderstorms like cumulus convection. Part two of the atmosphere is complex is that computers have a really hard time solving differential equations. They're really not good at calculus. And what that means is that we want a model that works everywhere, all the time. Solving a model for every point in time throughout the atmosphere and into the future is close to impossible, at least with the current amount of computer power that we have, maybe in the future. So what we do is we work in grid points. And grid points, as an example, you see the blue dots, they might just last you, but there are black and blue dots all over those two maps. So we put these grid points down, and we call that the resolution. So the resolution is the distance between the grid points. There are trade-offs for resolution. So you might sit there and say, why don't we just put more grid points down? That seems like a logical answer. Well, if you know, like when I was working on this presentation, the more you add to it, the slower the computer goes. The more we put into the computer, the more grid points we have, the slower that thing runs. It's creating thousands and thousands, we'll talk about that in a little bit, of calculations per second. So the closer you put those grid points together, the slower it goes. So we trade off. We have models that do both. We have small-scale models like the one on the right, and we have large-scale models like the one on the left. And we use both together to get a better picture. Because what happens with the small-scale models, like the one on the right, you have the grid points closer together. Since the computer has to go slower, you start to accumulate these errors, these little errors over time. But over time, over a 12-hour period, say, those little errors become really big errors. And over a week, they become huge errors. And then your model is totally done. But on the small scale, we can solve things better for point forecasting. For your point in time and space, we can do a much better job of where you are, what's going to happen. And we can also do better for things like thunderstorms, which are very complex processes to model. So we use both. So models are flawed, people are flawed, but when you put us together, we create a pretty decent forecast. We piggyback off each other, and we do all right. To give you an idea of the kind of computational power we're working with, because computers, like I said, have a huge advantage over our brains, the current model that we have, well, the current computers that we use, they can maintain 14 trillion calculations per second. I don't think I can do one per second, so, I mean, that's a definite advantage. And from that, we can get 14.8 generated model fields a day. So that is a humongous advantage. Even if it is incorrect, there's no way we could sit down and do all that math in the same time that the weather is going to arrive. They did this very early on, and they tried to calculate the forecast for the future, and it took them 7 days. That's a problem, because by 7 days you have to start over. So as an example, though, we constantly try to improve our accuracy, always. It's one of the National Weather Service's goals, is to always get better. On the right is from the National Hurricane Center, and this is a graph showing their annual average track errors. The National Hurricane Center relies heavily on operational models because it's really hard to model what happens over the ocean. The physical processes that happen over the ocean are a lot different than what happens over land, so we rely a lot on models. As you can see, though, over time, every single track forecast has gotten better, and each colored line represents the number of hours in the future the forecast is for. So from 24 to 120 hours in the future, we're consistently doing better. But if you look at it, like the red line alone, which is our 24-hour forecast, you're like, that's only 50 miles of forecast error. That's still big. That's the difference between Miami and Orlando for a hurricane. That's a big difference. But we are getting better. And like I said, it is their constant goal, especially at the Hurricane Center, to do better because, as we've seen, lives and a lot of dollars are on the line when these forecasts go wrong. So, what are you telling me? We're bad, forecasting is hard, but we're not as bad as you think. And on a day-to-day level, it may feel like that, but we really aren't when you average us over time. And let me reiterate that as much as everyone says we could be wrong every day and still keep our jobs, Congress really does not appreciate that. So the National Weather Service forecast offices have to produce a shareholders report. And they basically detail how well they've done and what they're doing to improve over the last year. And these graphs are from the 2011, because the 2012 hasn't been done yet, for our local forecast office, which is Peachtree City. And on the left, you see a mean temperature error graph. And if you look at it, what that's telling you is that over time, we've gotten better. Well, 2011 wasn't so good, but we've gotten better over time. And that truly, over a year, we're only 2.5 degrees off. That's fantastic, at least in my point of view. And then on the right, we have a first 12-hour temperature error. So one of the goals for this office in particular, and the goals for each office differ based on whatever they've decided, is that they will always forecast the high and the low between, within 3 degrees of what actually happened. So they go back and compare the observations to what they forecasted. And in 2011, they showed that they did that 81% of the time. That's a lot. That's a really good amount. They also reported that their temperature forecasts were perfect, i.e. 0-degree error, 16% of the time. Considering everything that we've talked about, I think that's great. We're doing a good job. Sometimes it just doesn't feel like that on a day-to-day basis. So our next myth. A 50% chance of rain is the same as flipping a coin. I hear that all the time. The weather forecaster comes on and says, oh, 50% chance of rain tomorrow. I have no idea what that means. So, let's figure it out. So, a chance of rain is officially known as a POP, or a probability of precipitation, which is the statistical probability that more than 0.01 inches, or a trace amount, of precipitation will fall in a given area at a given time. Those are important points. They have to be a given area and a given time. We're not just forecasting for the entire state of Georgia. That's crazy. And POP is calculated. I know, you're like, they just make that up. No, we actually use a calculation. So POP is C times A, which is C, confidence in the forecast, times A, the amount of the area, again, instead of given area, expected to receive precipitation if the precipitation occurs. So an example is if the forecaster is 100% confident that 80 or 50% of the area will receive precipitation of any kind, that could also be snow, then the POP is 50%, so our chance of rain is 50%. Or more likely, the confidence is percent and the area is 60%, 80 times 60, we get a probability of precipitation of 48%. We have a 48% chance of rain. So, but you said we needed a time frame and an area, and a lot of times what we get is that, which doesn't have a time frame, ever. Or they say, Atlanta has a 20% chance of rain. We already talked about that's a huge area. So we need something more than just a 20% chance of rain on Friday or Saturday. This is my personal recommendation to find your answers, to get a better detailed analysis of what they're predicting. If you go into the National Weather Service site, which is what I always recommend, not that I have anything against weather.com, Wonderground, AccuWeather, or the other 3 billion sites that are out there that forecast weather, I always recommend the source, which is National Weather Service. They have what's known as an hourly weather graph, which part of which you see here. And if you go down to the third block, there it's highlighted in red, which you probably can't see very well, but that's the best I could get it. There's a brown line that runs across the bottom, and that's precipitation potential. So that gives you the exact hours that they're expecting, the exact amount of rain, the exact precipitation potential. So in this case, this was from a while ago, but they were expecting between 9 a.m. and 6 p.m. on Friday, March 29th, a 6% chance of rain. Now we have a given time. And what you do usually when you put in your forecast for the National Weather Service, you have to put in a city or a zip code, and that is your given area. Okay, we've covered a lot of this so far. So, one of my favorites, and this is like my pet myth here, is that Ueber Doppler X, Y, and Z, or so-and-so's Doppler 9, or anyone's radar is accurate at street level and is live. Now, I hate to pick on TV weather forecasters, well, I don't, but they drive me crazy with this because they constantly perpetuate this myth, and they tell you, it's live, here's your street level, look, it's coming for you. That's ridiculous. So let's figure out why. First of all, we need to start a little bit with the basics. Weather radar is called many things. Weather radar, so-and-so's Ueber Doppler 9, NESTRAD. But it's all the same thing. Radar is actually an acronym. It stands for radio detection and ranging. And the radar we use to look at weather specifically is a Doppler radar, meaning that we can see location and motion of particles that are happening within the air. We have 155 Doppler radars in the United States as well as Puerto Rico and Cuba. And we've been using them since the 1940s, although that was a lot to do more with the war than weather. But we do have technology back to the 40s. So, how does radar work? The radar sends out a pulse of energy, and then we listen for the return. Based on how long it takes that return to come back, we can calculate the distance from the radar, which is how we get that nice plot that we saw in the first slide, where it shows us where the location is and the intensity. We also keep track of the phase in return so that we can understand the motion and how things are propagating through the atmosphere. And then we take all that information to the magic computers and we plot it on a handy little graph and post it to whatever source you're looking at, whether that's on your mobile phone or on the National Weather Service site. So, radar is never live because I just said we have to listen for a return. We have to wait for that energy to come back to us. Now, I will give you that takes a very quick amount of time. We're not talking minutes for that to get back or anything longer. It's very quick. But we still have to listen for that return. Inherently, that is not live. We also have the problem that radar does not just do one little scan and send all the energy back and process. That's inefficient and very ineffective and a lot more costly. So what we do is we program volume coverage patterns, or VCPs, into the radar's processing software, and that tells the radar exactly how to move through the atmosphere. One such VCP is at the bottom. It scans each elevation angle, which is shown by different colors, in a 360-degree, and then ticks up, and then scans the next elevation angle, and then ticks up, and then does it again, until we get to the top, and then we post-process. So, the one that's on the bottom of the screen actually takes 5 minutes to complete. We use these in what we call precipitation mode, when meteorologists need to see quickly what's happening in the atmosphere. These are things like when we have severe storms. In a clear air mode, which is when we really have no precipitation out there, it takes about 10 minutes to complete the volume coverage pattern, because we're really, really trying to find that precipitation in the air. So we really need to scan more in depth and more time. So if it takes 5 to 10 minutes to scan, and we have post-processing time, you're looking at a radar return that is at least 10 to 15 minutes old. That's not a huge problem for the general public, but it's something to keep in mind when they keep telling you that it's live. Second part of this myth is that it's accurate to street level. This can also not be correct. As we propagate from the radar center, the radar beam occurs what's known as refraction. It bends because of the way the Earth's surface and the Earth's atmosphere interact with each other and the energy. So that means that as it goes farther, you're no longer looking at the same place in the atmosphere that you were closer to the radar. So at 20 miles, you're looking at a much lower part of the atmosphere than you are at 50 or 100 miles away. And that basically means to you that what you're looking at might be more intense or less intense than what's actually falling out of the cloud. And we have another problem with that. As the radar beam propagates away from its source, it also spreads. Beam spreading. I know. Very good. They were very thoughtful in that. But what that means is that storms can appear differently on radar based upon where they are in relationship to the radar center. As shown in the picture, we have two storms, and they're both exactly the same size, but they're some ways apart. Storm 1 is going to look a lot bigger and a lot more intense on radar than Storm 2, because Storm 1 fills up more of the beam than Storm 2 does, even though they're exactly the same size. But how big of a problem really is this? So this is a chart showing sort of our area. As I said, the radar unit is based in Peachtree City. Peachtree City is about 30 miles or so south of Metro Atlanta. Not really here, Martin. But we can see what happens to the beam through propagation. We have top height, center height, and bottom height, as well as on the right we have the beam width category. So you can see that in Noonan or Fayetteville, somewhere about 10 miles from the radar site, the beam width is just a little less than 1,000 feet. So by the time we get up here to Beaufort or Lawrenceville, the beam width is over a mile wide. So simply by that fact, a mile is much different than 1,000 feet and probably not directly at your location. So we can't be accurate really to street level when we're saying that the beam now is a mile wide or 1,000 feet wide or 2,500 feet wide. And that center height also gives you an indication of what happens when I was talking about that refraction. At 10 miles, the radar is looking about 600 feet in its center line in the air. And then at 16 nautical miles away, we're looking at, a mile up. So it changes a lot, even in our local area. So, why do you care? Again, I try to bring this back to you guys because I think that's the most important part is whether it happens to you every day. So how do we use this better? Radar is a fantastic tool, and I'm not trying to tell you that it isn't because it represents a huge amount of time, money, and research all towards the common goal of better forecasts and therefore public safety, which is a noble goal. But what I'm telling you is use radar as a guide. Don't plan your day around it. And when the little man comes on the TV and says, oh, it's headed for this street and not your street, yeah, still go inside and cover yourself with a mattress, because it's not going to be that accurate. And you don't want to be stuck with a tornado in your face when you could have been inside. Okay, so use it as a guide. Make sure you're following those watches and warnings that the National Weather Service produces, because they know about this and they want everyone to be safe. It also represents great things for seeing trends. So if you know, oh, the rain is coming, when is it approximately going to get here? It's great for that. Just don't plan it to the minute. That will not work out for you. Okay. This one I need to preface a little bit, because I'm not sure what we have here as a crowd. But I come from meteorology, I come from science. Global warming and climate change are happening. I'm presenting to you facts and data that have been documented and researched a lot of times over. I'm not going to try to sway you on anything. All I'm doing is presenting facts. Okay, so the judgment is up to you whether or not you believe in it. I'm just going to present facts. Yes, this is an Alaskan glacier, and they were both taken in August. You can see a lot of melting already in here. So, as always, I'll start a little bit with the basics. Let's define some terms, because these get interchanged and used like they can be interchanged, but they're not the same term. Climate change, and these are the definitions from NOAA. These are not ones I made up. But climate change is a non-random change that is measured over several decades. Decades is the key word here. Climate change is not about daily meteorology, and that's where we get into climatology, which is the study of climate or trends over time, not day-to-day weather patterns. As you can see, they do say the change may be due to natural or human-induced causes. Climate change happens all the time. Global warming, however, is an overall increase in world temperatures caused by additional heat being trapped by greenhouse gases. So, what are greenhouse gases again? Greenhouse gases are those that absorb terrestrial radiation and contribute to the greenhouse effect, which include water vapor, methane, carbon dioxide, and ozone. The greenhouse effect is very necessary for our planet and for you to live here. Without the greenhouse effect, the average temperature on Earth would be 0 degrees Fahrenheit instead of a balmy 57, 59. On the right, we see the diagram from NOAA of how the greenhouse effect works. So all of our weather comes from solar radiation. All of our heat basically comes from solar radiation. And that incoming radiation gets trapped and gets re-radiated in some places. About 30% of the incoming radiation is radiated back into space. 20% is absorbed by the greenhouse gases into the atmosphere. And the other 50% is absorbed by our surface. So the problem is not that we have greenhouse gases, it's the amount of greenhouse gases that are in the atmosphere. Okay, some people get iffy about this. Well, I'm going to put it out there and say that humans have increased the amount of greenhouse gases on this earth. There is no scientific debate on this fact. I say again scientific because a lot of people will debate you on this. But we have increased the amount of carbon dioxide in the atmosphere. And that's mostly the greenhouse gas that we affect, is carbon dioxide, because it comes directly from the combustion of coal, oil, and gases. This very long-term chart goes back over 400,000 years, and we see the carbon dioxide concentration measured in parts per million by volume, which is that ppmv. Over time, the flux of CO2 has changed. It's gone up, it's gone down, a lot. What we have never seen in over 650,000 years is a concentration above 300 parts per million per volume, and it's still climbing. The global temperature is rising. This is a shorter range graph, but what we see here is an increase of 1.4 degrees Fahrenheit since the early 20th century and before that. In the middle is a faint line, but that's the average temperature from 1901 to 2000. And the blue and red are then based off of the average temperature, whether the temperature for that year was above or below the average. You can see a lot of that and yearly fluctuations in temperature, and that's perfectly natural. We see that all the time throughout recorded history and unrecorded history. We also have a plot of our CO2 concentration, and the main thing that you should notice is that both increase. As the CO2 concentration has gone up, our global temperature has also increased. Some of those yearly fluctuations can be attributed to a lot of different things. Large volcanic eruptions cause global cooling due to the blanketing effect in the atmosphere. Perfectly natural processes that occur all the time, El Nino and La Nina, cause global cooling and warming as well. But again, we're talking about long-range terms, not year to year. So on average, we see that the global temperature is rising. Now, you say 1.4 degrees. Man, the daily temperature goes up 30, 40 degrees sometimes. What is the problem with 1.4 degrees? Well, remember, this is an average over the globe. This is not just in Georgia, it's not just in the United States, this is the global average. So what we see, especially in like the Arctic, is we have massive fluctuations in temperature, massive increases, and we see massive decreases in other parts of the globe. As well as, if you want some context, our last ice age, a ways ago, was only 5 to 9 degrees globally cooler than what we are having now. And that's when the Earth was covered in ice. So when the Earth's temperature changes a little bit, it has massive repercussions for everyone. Sea level is rising. The graph shows, again, sort of a shorter term as far as sea level rise. So what we see now is that it's rising at about 1.7 millimeters per year for the past 100 years. And then since 93, we've seen 3.5 millimeters per year. Again, 3.5 millimeters is like, itty space. But, again, globally and over time, that's a big problem. And I'm sure a lot of you have heard about sea level rise and, you know, Florida going under and all things that are crazy. But over time, those things are able to happen. A lot of this rise is attributed to increased temperatures because what happens if you haven't taken thermodynamics, or if you have, warmer water is volumetrically larger than colder water. So as the temperature increases, the water goes up. Sea ice is decreasing. This on the left, or on the right, on the right is a chart from September 2012, which was the most recent summer minimum for sea ice. And what they have reported is that Arctic sea ice in 2012 was 18% smaller than the previous record, which was set in 2007. 2012, we shrank 1.3 million square miles of ice, smaller than 2007. And this is 50% smaller than the long-term average of 1979 to 2000. Unfortunately, shrinking sea ice is a vicious cycle. As you see on the left is albedo, and that's a term which basically reflects the average reflection of an object. So this is, again, the black hole. As the sea ice melts, it lowers the albedo and changes how much absorption we get into the Arctic Sea. As we have more absorption, the temperature increases, more sea ice melts. And also, the problem with that, and you've probably heard of this too, is that this changes not only the temperature, but the local ecology of the sea ice. And the most notable example is the polar bear, who uses sea ice to hunt. Without sea ice, he can't hunt, he starves, and eventually we see species extinction. Another indicator in long-term changes in the Arctic is the age of the ice. And we have seen a very steady decline in older ice. Older ice is important because it's thicker and can withstand long-term changes in temperature fluctuations much better than newer ice. We track the age of the ice using satellite and buoy data observations, and that's been done since the early 1980s. And for the month of March, when the sea ice is at its maximum, older ice, which we classify as 4 years or older, has decreased down to 7% of all Arctic sea ice. down from 26% in 1988. And you see that was down from 19% in 2005. And that represents a decrease in over 1.7 million kilometers squared of ice lost only since 2005. That's a humongous amount of ice. A lot of people note and attribute global warming to solar output and an increase in solar output. And this is not a far-fetched idea. As we get a lot of our weather and radiation, well, pretty much all of our radiation from the sun, if radiation were to change, you would think the global temperature would go up. It makes total sense. But we have been monitoring the sun for about the last 40 years using satellites, and you can see that on the graph on the right. The solar output goes in 11-year cycles. It increases, it decreases. What we haven't seen is a correlation with global surface temperature. So right now our temperature is still increasing, but the solar output has not been for a long time. We're starting to ramp up again into a heavy solar cycle. However, I will caveat that we don't have a good long-term use of evidence for the sun. Obviously, we didn't have satellites in the 1700s. We had ice cores, we had tree rings, and that's how we studied CO2 parts per million. We didn't have anything to monitor to the sun, but they're working on that, and they're really trying to find a long-term source for solar output because it is important to know what's happening, whether it is global warming or the cause or not. We need to know what's happening with our sun. And this is the point that I make to everyone that I ever talk to about climate change and global warming. It's not that we haven't experienced change. We have. The Earth has been through so many changes. It's gone through ice ages. It came out of it. It's seen fluxes in solar output, like we just talked about. The temperature has increased and decreased. A lot has happened to this Earth. But right now, it's the rate and extent. And this is from the IPCC, which is the Intergovernmental on Climate Change, which is a collaboration of over 185 countries and scientists that have come together voluntarily to study the climate. They've been doing that since the 70s. It's not a new thing. And they put together a report all the time. Now, I'm not saying go out and read it. It's huge. I mean, it's a big report. But they do take a lot of time putting this report together using peer-reviewed processes, meaning that people review each other's work. It's not just Joe Schmo saying, yeah, the time's changing because I found a rock saying that it was. Like, no, this is documented research. It's been peer-reviewed. It's been studied a million times over. But from what they are saying, and they're also charged with putting together socioeconomic as well as environmental impacts from climate change, is that if things continue, we'll see things like decreased snowpack, increased heat waves, species extinction, like we talked about with polar bear, significant changes in water availability, increased flash floods, increased severe weather events, all kinds of really not fun things. But you can make a difference. Yay! Everybody says recycle, but seriously, it's really not hard. It saves so much. Even on you can save money by recycling, and it's really great for the Earth. Using responsible transportation methods, carpooling, walking, using mass transit like MARTA, using energy-efficient products like CS light bulbs, reusable shopping bags, Energy Star appliances. In fact, Energy Star and the EPA have rated that if you replace 5 of your most frequent, you can save $70 a year on energy bills, and they last for like 10 years. So these are really great things to do. Please be informed. Do your research, but do your research from reputable websites. Don't just go out and type climate change hoax and read the first thing that you get to. I've read many. There are plenty of terrible websites. A lot of them doctor their information and charts. Like I've seen side-by-side graphs where they clearly doctored the information. Use reputable websites. NOAA, the National Weather Service, the EPA. all these government websites, including governments outside of yours, if you feel it's a government conspiracy, have documented research on these things. Again, the IPCC, all of their stuff is online. You can go and read so much about it. And if you learned something today, which I hope that you did, please pass along what you learned. Even if you just learned, I can save a lot of money by using energy efficient appliances. Awesome. Go tell someone. And tell someone to do their research too, because there are a lot of people that are just uninformed. And it's not their fault, but they need to be informed. So, at that point, I will take any and all questions. My email address is up there. If you want to shoot me an email about a question you feel scared to ask, I would be happy to answer it. If you want to discuss things in length, I can also give you websites where you can read any of the topics we talked about today. So, questions? Anyone?
I'm hoping for the online people too.
One of your graphs, when you were talking about carbon dioxide increases, and we went back, I think, 400,000 years. How do we know what the carbon dioxide levels were 400,000 years?
We use a variety of sources for this information, to include tree rings, Arctic and Antarctic ice cores, skeletons and coral reefs, as well as soil sediments. The most notable and probably the most heard about is the Antarctic and Arctic ice cores, and they drill into the ice, and it gives us ozone molecules that were trapped in there thousands of years ago, and they can go in and remove those molecules and study what the atmosphere, a picture of the atmosphere looks like based on that little bit of molecule. Anyone else? So easy. Nobody wants to fight with me about global warming?
Okay, no, but there's a comment, but the portion of global warming was fascinating. So thanks for bringing that up. It was also very urgent and timely.
Nobody else? Well, I always encourage you to get your weather from National Weather Service. They really are the source of everything weather. And just do your homework and make sure you know what you're talking about.
Find out for yourself.
You wanted to add another